Oy, 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 oy. Oy, 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 oy. Oy, 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 oy. Oh. So, what are we doing? God damn it. Hold on, I just need to take care of something. was like 1,000 years ago. I gotta find something real quick. I just realized. That one. Something like that. All right. Back to this. So, we're now basically back to where we were. We have a bunch of issues. I wonder if it's that bad. No, yeah, there it is. I think I fixed it a little bit, but not really. I think we just need to continue implementing this. But I'm not sure. But this is weird here. Why isn't there a try here? Because like here there's a try. But it says a none too, for some fucking reason. Huh? Why is the try called none? It's clearly there. Right? But it's just none. Huh. And it's clearly right. This is none. Oh. This is so stupid. The annoying part here is it's just like infinity special cases, right? And that's what makes it really, really tedious and annoying. And like it sounds so easy when you just think of the concept. You're like, okay, yeah, you just like connect the voxels together and it's, you know, whatever. But it's not so simple. It just isn't. Like every technique involves some kind of meshing. And it's messy. It really is. Because that means you have to decide, you have to like implement the shapes somehow. I was looking at SDFs and stuff as well, but I just cannot think of how an SDF would help me in any way. It just doesn't. But I find almost every resource on SDFs and like every video and presentation to be very difficult to like apply. Because it's like for some project that's designed for their project. So it's like, okay, but how do I really adopt any of this? That's really hard. Because if I could use an SDF in a way that felt like it made sense, then sure, like why not? But I don't think I really can. And at the end of the day, I think that I have to do meshing. Like in one way or another, I have to do meshing because whatever, like, if I want to be able to build a house and I want that house to be able to have special shaped building pieces in any way, those have to be, they have to exist in some form, right? So I like either it's meshing or it's like built up out of voxels at like a size that's a tenth the size of the rest of the voxel grid, and then that's like smoothed somehow. But then that has to be smoothed in a way that supports texturing and doesn't run like ass, right? And that's what's so hard, and I'm not really sure what the approach is. Because I feel like I could kind of do something like this here, and then I have like a micro voxel grid as well in local areas. And then use kind of the same technique here, but I think that's bad. And there's a question of like data limits too, right? I actually don't know what I'm gonna do this stream. We might just continue trying to work on this, but I'm a little unsure. Because if we look at like a marching cube solution, for example, it's just full of bullshit. Like, this is bullshit. Like, there are only 15 unique cases, sure, but even so, like, what the fuck are these shapes? Where would I ever need this? I don't even understand how this exists. Like, what is this? This is some weird ass. This is like to connect. With like something that's, I don't even know what this is supposed to be. Triangles here, here, here. I don't know, bro. This is so far beyond what I really want. I think what I'm doing is like the only thing. Does it say if all 8 vertices of the cube are positive, or or all 8 vertices are negative. It's so poorly written, it doesn't even mean anything. Like this only means something if you already know what it means. Marching cubes is a simple algorithm for creating a triangle mesh for an implicit function. It works by iterating marching over a uniform grid of cubes, superimposed over a region of the function. If all 8 vertices of the cube are positive or all 8 vertices are negative, the cube is entirely above or entirely below the surface, and no triangles are emitted. Okay, this is information that hasn't even been presented yet. Okay, they're positive and negative. It's based on some bullshit. Okay. As a simple example, the function x squared plus y squared plus z squared minus 1 equals 0 represents the unit sphere. Okay. Absolutely horrendous. If one vertex is above the isosurface, and an adjacent vertex is below the isosurface, then we know the isosurface cuts the edge between these two vertices. What the fuck is the isosurface? To an isosurface is to form a facet approximation to an isosurface through a scalar field sampled on a rectangular 3D grid. Given one grid cell defined by its vertices and scalar values at each vertex, it is necessary to create planar facets that best represent the isosurface through that grid cell. I have long understood that there's a very huge difference between not understanding something because you're stupid and not understanding something because it's fucking nonsense and written by someone who can't write. And almost everything that I ever read when it comes to this kind of stuff is like some fucking gobbledygook. Like, it's not written to be understood. It's written to, like, be read by the writer and understood by the writer. It's not written to be understood by anyone else. It's just a bunch of bullshit. What the fuck is an isosurface? Like, An isosurface is a three-dimensional analog of an isoline. Fuck you. An isosurface is a 3D surface representing points of a constant value within a volume of data. It is the 3D equivalent of a 2D contour line. Okay. So it's just the surface. Okay. Edge vertex. Edge index, vertex index. Okay, so it's got edge indices and vertex indices. If one vertex is above the isosurface, so are we creating the isosurface by the center of the voxel? So everything passes through the center, and therefore the bottom vertices can be negative and the top vertices can be positive on the surface voxel. So they just have to be -1 or +1. If, for example, the value at vertex 3 is below the isosurface value, and all the values at all the other vertices were above the isosurface value, then we would create a triangular facet which cuts through edges 2, 3, and 11. Okay. Yeah, I do understand. Can I use this? I mean, obviously I could use this. But this, again, this does not support volume. It just doesn't. And this does become difficult because since this isn't really about setting the shape of the cube. This is about creating a shape based on a surface. Right. Whereas what I'm trying to do is I have a cube and I'm trying to just like reshape it to connect to nearby cubes. And the difference is that here you can have basically two cubes in the same cube. Because that's what this stuff is on the previous one. You had unique shapes. Bullshit shapes. Like two planes next to each other. That's because that's actually two different surfaces that are kind of closing in on each other there. But it's, I mean, I feel like it's actually not that heavy to do marching cubes, is it? It's what, like 16 bits per voxel? It's not that bad. Or is it more? Like we have vertex indices, right? And we have edge indices. This is not a very good example. ISO level. Fuck is the ISO level? An 8-bit index is formed where each bit corresponds to a vertex. If grid value 7, looking up the edge table returns a 12-bit number, each bit corresponding to an edge. 0 if the edge isn't cut by the ISO surface. Intersection points are now calculated by linear interpolation. I don't understand. Yeah, I still barely understand. I'll be honest. The ISO value. ISO surface facet. ISO level. I don't understand how they're like, where is that value coming from? The fucking ISO value, man. The user specified ISO value. ISO value. Like, it's just some bullshit. What the fuck is the ISO value, man? Fuck you. Is that the grid size? No, it's not. So it's user specified now. I thought the ISO value had to do with the value of the ISO surface. Interpolated locations will obviously give you better shading, blah 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 blah. $1997, bro. There's gotta be a better article about this bullshit. An ISO surface value. The algorithm requires a data volume and an ISO surface value. For example, in CT imaging, Hounsfield units of +700 to +3000 represent bone. So one potential input would be a reconstructed CT set of data, and the value of +700 to extract a mesh for regions of bone and bone-like density. I think these articles might be poisoned with bullshit. I think the ISO surface value is a threshold, a cutoff point. and each voxel has a density in these, because this is the marching cube algorithm is designed for medical application. So that's what it's about. It's about getting CT scan data and then filtering out low density areas and then creating a spatial image or spatial model of the more dense data, right? That's pretty much what it's doing, I think. So the whole ISO surface value that they were jabbering on about, that's like some outside information that they just expect you to have. And what that means is that we don't have an ISO surface value. Because it's either there is or there isn't, right? It's 0, 1 or 0. So our ISO surface value is just 1. Spacing Quark. This implementation also works correctly on anisotropic datasets where the voxel spacing is not equal for every spatial dimension. I don't know what we're building. Oh. But it almost sounds like they're trying to tell me that we can have differences. In like volume and central positioning, kind of. Oh my god. Failed? Oh, bro. A scalar value. Every vertex is supposed to have... Every vertex must have a scalar value. That sounds heavy as hell. The heck? Like, how would that help? Like, it's... just doesn't... just don't get it. I'm just what I don't understand is like, what is the level of precision? Because it they make it sound like it can find varying intersection points, but I don't know, like, this shape here, can this exist in a way where it's like further away? Because that would mean that that's where this would have a scalar, right? But oh, the scalar values on each vertex, that would eat up infinity amounts of data. Like, there's no way. Triangulating the 256 cases is possible, but tedious and error prone. Yeah, that's kind of what I was doing before. Here. We create an index for each case, based on the state of the vertex. Yep. This index serves as a pointer into an edge table that gives all edge intersections for a given cube configuration. Using the index to tell which edge the surface intersects, we can interpolate the surface intersection along the edge. We use linear interpolation, but have experimented with higher degree interpolations. Since the algorithm produces at least one and as many as 4 triangles per cube, the higher degree surfaces show little improvement over linear interpolation. I mean, I don't really understand what they're saying here. They interpolate the surface intersection along the edge. Does that just mean like they're just creating an edge from here to here to here, or are they saying that the edge can be like somewhere in between? Because that's the reality, right? Like, just because this one is intersected, or just because one is positive and the others are negative, or rather this one is negative and all of these are positive, the edge can still be like up here. Can it not? I mean, maybe not. Maybe it can't if we, because it depends, right? If the ISO surface is just cubes and triangles, right? Then it might not be able to intersect anywhere other than the center. So that's just how it is. But like, what kind of shape would that be? How would that... This is the triangle. Yeah, okay. This is the edge that I implemented. That's the fake triangle. That's what this is. Kind of. Oh. Using the densities at each edge vertex. This is where I'm so confused. I feel like it's... Because I feel like it's just a cutoff point. I don't understand how the density really ties into this, because it should just be a cutoff point as to which voxel is valid. So I don't know why they talk about densities and interpolation. Using the index to tell which edge the surface intersects, we can interpolate the surface intersection along the edge. I don't understand. Can be interpolated to get actual smooth terrain, but without, you can do linear slopes. But like, I don't get it. Like, what are we interpolating? Like, we're using the densities, but... Huh? the gradient vector at the surface of interest. We first estimate the gradient vectors at the cube vertices and linearly interpolate the gradient at the point of intersection. The gradient at cube vertex ijk is estimated by using central differences along the 3 coordinate axes. Where dijk is the density at pixel ij. In slice k and delta xyz are the lengths of the cube edges. Dividing the gradient by its length produces the unit normal at the vertex required for rendering. We linearly interpolate the normal the point of intersection. Note that to calculate the gradient at all vertices of the cube, we keep 4 slices in memory at once. I'm just having a hard time understanding. Because they talk about density and stuff, and that has to do with the fact that this is medical science, right? So you have a bunch of voxels. I don't know how to really represent this, but... And then you give them values. Let's say that these are like 1, 1, 1, 1, 1, 1, 1. This is a 3, 4, 3, 2, 1, 2, 1, 1, 3, 1, 1, 1, 1, whatever. And then we say like the cutoff point for creating an isosurface is 3, in which case you're gonna get a surface that looks like that here. But then we're talking about density at certain vertices. And I'm just super confused. Or is it more like this? Yeah, because it works like this, right? It's not like that, it's like this. This is what it looks like. Kind of. If there was a little bit more accuracy here, it would make a bit more sense, maybe. Because it's not... We're not finding cubes, we're finding points. And as such, here then, this over here the density here, what's that supposed to be? Is the density here like all of these 4 combined divided by 4, kind of? That would be a linear interpolation, right? Like, is that the idea? I don't know. I just don't really get it. Because in this case, this would be like... Sure. I'm just not very happy with really any documentation I've found on marching cubes. I don't feel like it really helps. To illustrate an ISO curve, imagine the first picture is a cross-section ocean image on a 2D grid. Yeah. Where the blue vertex indicates a data point within the ocean. To create an ISO surface, an ISO curve from the set of blue data points, the marching squares algorithm constructs conceptual squares and marches through each square, drawing linear lines separating the blue vertices from the rest of the square. Squares with all blue vertices or without any blue vertices are completely in or out of the ocean and therefore are not part of the curve and require no drawing. Squares with 1, 2, or 3 blue vertices must be part of the ISO curve and require drawing. Drawing constitutes a line between the centers of the edge with only one blue. Right. So far, this is much better. Actually understandable. Using this methodology, constructing an ISO curve from our 2D image of the ocean looks like this. Not a great fit. We'll discuss shrinking the grid size for improved accuracy later. Instead of an ocean, we'll look at a circle. Yeah. First picture shows a black circle in a 2D grid with vertices inside the circle. For each vertex combination, one line, two lines, or no lines should be drawn between the edge centers of the square. Reading two adjacent data lines to form squares and commence marching through the row of squares. Because I feel like it would be ideal if I could just use marching cubes. Because that's like... it's a system that already exists. And the implementations exist. It's just there, right? Non-Boolean datasets. Vertices can hold specific numeric values beyond the Boolean value of in or out. These values could conceptually represent anything: a color, a substrate density, type of body tissue, etc., as one would suspect. However, when we add values to the edge vertices, the vertex for the isocurve intersection should cross closer to the vertex with the value closest to the threshold criteria. Let's look at an example. Imagine a threshold criterion of less than 32 Fahrenheit and data values at each vertex, indicating the degrees Fahrenheit at that point in the 2D space. Using our previous method on this square, we would get the following. Clearly, the isocurve line should go closer to the vertex with a value of 30f than the vertex with 50f. But the drawn line puts equal distance from the isocurve intersection in each vertex. Linearly interpolating between the two vertices solves this problem and gives a result similar to the following. Okay. So to make sense of this, right? In order to get these values, that's where I'm like a little bit. This we've got vertices here with 30, 35, 35, 50f. Those values are like voxel points. But that's what's weird, because the middle here should be the voxel point. I know. Like it isn't, but that's what's weird, right? Because again, this is supposed to be used with medical data mainly, or that's the original idea, I think. And that means that you have density like this. And so we are smooth type of noise, hence we get the gradient. Yeah, but yeah, that's kind of what I mean. Like here, I think it was kind of like what I said originally. Like if the cutoff point here is, let's say it's 2, we include the 2 there, we would get something that looks like this then. Well, it's I think let's make this make a bit more sense. Let's do this. And then we say that these are like 3s. Yeah, I don't understand my drawing either. That's okay. This is just supposed to be a representation of density data. Like imagine this is a CT scan and this is a data grid where each voxel has a density based on what we got. And so we'd end up with something like this if the cutoff point was 2. I think it would go diagonally like this. And this is then the isosurface. And then we create, so we do create voxels around this. I think. And then we give each vertex of the voxel a value. I think. Because then, in order to get the gradient, we'd have to give this corner a value based on its neighbors. So it would be 3 plus 3 plus 3 plus 4 divided by 4. And that's what the gradient value would be in this corner. Because then that would translate into this. Because that would be like, we have like 50 Fahrenheit in here, and up here it's also 50, 50, 50. Then over here it's like 10, 10, 10, whatever. And then here in the corners, it would be then the interpolated value between this point and that point that we would end up with here. Because, as you say, normally, we would have some kind of noise map that we're actually trying to generate a model out of. And that noise map is a much higher resolution than whatever voxels that we're trying to build it out of. And since we don't have a noise map, we then have to create the gradient by sampling neighbors and then creating some kind of interpolated value in between. I think. Because I can't be using like a noise, because that doesn't make any sense. Like, that's not how things work. So we can't use that logic exactly. And in order to do this, like, I understand the interpolation. Linear interpolation isn't hard to understand. It was the fact of like what they were doing. Because before in the other articles, they were just kind of doing it, right? And there was a lot of assumptions going on that I understood something there. And there was a lot of missing info, I felt like. So with this it makes a bit more sense. Linearly interpolating between the two vertices. The isocurve line should go closer to the vertex with a 30f than the vertex with 50f. Threshold equals 32 degrees. I'm just trying, like, I do understand, because here where it's just getting centered between 50 and 30, but we know that the value we want is 32, so we can just calculate where 32 is between these two values, right? And then we just use that. Like that makes sense. I'm just trying to figure out how I could translate this to kind of the opposite in a way. I wouldn't have a cutoff point. Would I? Because the cutoff point would be 0 or 1, depending on how you look at it, inclusive or exclusive. And then up here it would be 0, and here it would be like 3. And the maximum value would be 7, or like the density of the voxel, I guess we can call it, even though it's the volume of the materia inside. What would be the domain you're sampling in your case? I mean, it's kind of... I would be sampling a height map, really, I guess. Like, I'm creating a voxel matrix using a Perlin noise map. So that creates a bunch of voxels with a density that ranges between 1 and 7, or 1 and 8. And 0 is empty space, right? So I guess it would be like because if this is 0, let's say that's 0 and this is 3. Because this would be the scenario, right? Like if we look at the normal marching cubes scenario, because you're using a cutoff point, you're going to have data outside, right? And then you can use the outside data to interpolate. But in my case, the outside data is always going to be 0. And in that case, if this is 0 and this is 3, that means that the interpolation is actually going to be between max and this value, I think. And in this case, max is 8. So that way we can figure out that this point is going to be at 3 divided by 8 along the edge. Which would be like there or something. But this is an SDF. Kind of. And that's a huge amount of data. The Perlin noise isn't really the basis. Right now I'm just using Perlin noise in order to create the terrain. So the real basis of this is that I have a voxel matrix where each voxel has a volume between 1 and 8. And that's what I want to use, and that's what I want to represent. That's really the data that we're working with. The Perlin noise is just a method to get to that point that I'm using now as like a crutch. And then we do DDA on the GPU, yeah. But what worries me about this, right, is that maybe it won't be that much. Like, maybe it's not that bad. Like, I think it's kind of bad, but because right now I have three bits. That's 3 times 8. That's 24 bits for each corner. I think that's acceptable. That's not horrendous. And I don't actually need that either, because I could calculate it by fetching the neighbor, but I don't know how shitty a load is. That's the thing. So like that's what I have been doing. I'm loading every single neighbor, and that's the difference, right? Like either I bake the values into the voxel itself, or I load its neighbors and I do the interpolation in the rendering step, which is not good, but it's one of those things, weighing data versus execution time. Because 24 bits does add up, but I think it's an acceptable amount. So I mean that would basically translate to having 64. I think I would have about 64 bits per voxel. And then if we have 1000 times 1000 times 100 times 64, I don't know what that is. That's 800 megs. That's fine. That's completely acceptable. Maybe I should just do marching cubes. Because I was of the mind that marching cubes were more rigid, that it wouldn't really support what I really wanted to do, which is the ability to, like, let's say let's say that the world is a density grid, right? And we are shaping it based on the density, or we're shaping the ISO surface based on the density, right? I want to be able to like dig into the ground and have it deform based on the volume inside of the voxel until the voxel disappears because it becomes empty. As opposed to how it is in like Minecraft or something where the voxel is either there or not. That's like a very core thing that I want to do. And I was sure that Marching Cubes didn't support that, but it seems like it does. Because one of my current concerns is that how big is my current voxel? My current voxel is actually way too big. It's 96 bits. Because I'm storing the brick index there, which is stupid. I shouldn't be doing that. And because of that, right now I'm generating a map that's it's only this big. That's only 452 megabytes. That's so weird. Huh? It's not bigger than that? It was crashing my CPU, or my GPU. Is that real? That should mean that I should be able to say we have a view distance of like 20. Like I should have space for like 40 view distance here. It's gonna take literally like an hour to generate. Yeah. I'm a bit at a crossroads. Like, I don't really know which direction to take. Because I know there are some difficulties with Marching Cubes. But I don't think that it's that bad, because like, when it comes to like recalculating it, it's just gonna be like the modified space just needs to be recalculated and that's it. Otherwise it should be fine, and there's no like massive amounts of redrawing. The one thing I have seen that people mention is that it doesn't support LOD very well, but I feel like that depends really on how you do it. There are some methods. There's also something called like transvoxels or something, which is supposed to be an additional like variant of the Marching Cubes, which supports LOD better by like stitching two resolutions together. Why are you... How is it freezing? All right. Well, that actually works. All right. One of the things I really would like as well is to be able to have long view distance. That's honestly one of the goals for why I'm doing Raymarching in the first place. Being able to have significant draw distances. But right now, like, this is a draw distance of... and then you have to divide it by 2. So this is like 640 voxels if we're standing in the center. And that's not even particularly good, I think. That's like 80 chunks in Minecraft. That's like basic. And here it's running at 59, 70, 60, which is really bad. Like really, really bad. So if I can actually do marching cubes without it significantly impacting memory, that would mean that I can remove pretty much every single calculation, and I can remove every single load, and that's just gonna run super well compared to this. Because that's like... right now it's just horrendous. And there's so many like ifs and shit too. I don't know. I have to load, I have to calculate neighbors, and there's multiplication and all kind of nonsense. I am leaning more towards this now, I'll be honest. So it's 8 bits. Essentially, your density value is your domain you're sampling, right? I don't really understand why the value has to be carried over to the voxel. Why don't we just sample the same domain for DDA and MC? Well, because the... because the voxel is the density, right? Like, that's... because like, I want to generate the world in some manner that will generate a voxel matrix with voxels of varying density depending on what the terrain is supposed to look like, right? That's why the density or the volume is stored inside of each voxel. Is it some kind of sparse story? No. I mean, it's just voxels. It's just Minecraft with volume in each voxel, so that we can use the volume to represent its current size, or like how much stuff is inside of the voxel. And so I don't really want to have like a separate like noise map or something, because then I would have to edit that when we edit the voxels in the game. So I'll be honest, I'm not really sure where the confusion is either. Something I would be worried about though is what if we enter a voxel and the geo is at a grazing angle with the view direction. Now we have to DDA again when we exit over and over. I think I know what you're talking about. Maybe. Oh, yeah. Oh, you are you talking about, because there are things where, like when a line is really straight, there are some issues, because then you get like a delta distance of 0 or some bullshit, and it like breaks, which you can fix with some workarounds. But there's also just the fact that if you're using like sparse volumes to accelerate the ray, and you then look at like a line of empty voxels, and it makes us jump through like each voxel forever because we never enter accelerated space. Is that the kind of scenario that you're... Yeah. Yeah, that is a concern, but it's not that big of a deal. Like we do have to test, and yeah, because it's that issue, but it doubles up, because if you are like, if you're using just normal cube voxels, then if you are looking through like a corridor, for example, you always have to iterate in voxel space, and that fucks up the performance. But since I am making voxels that have shape internally, that means I have to basically do triangle checks in each step as well, right? And that's, yeah, that would suck for sure. But I haven't noticed it that badly. I think it's, I think the concern for that is a little overblown, at least nowadays. I think it was more of an issue like 5 years ago, but like if you compare a 1060 to a 4060, I feel like they're powerful enough to make it like not really matter. because I feel like it kind of makes up for itself a little bit, because the closer you get, the more rays also actually intersect with the ground. So you do lose a bunch of rays that you don't need to continue calculating. So I don't know if it's really that big of a deal. But I have been considering like solutions to it, but I don't think there really are many good ones. You know, like creating like empty space, basically like indexing the empty space so that you can just check like, okay, how far is this empty space going to be, and that way you can skip the empty space in like a long line with straight rays. But that completely breaks at an angle. I think it would actually work to do something like that, but it also requires a bunch of data to do that. So I don't know. Like, if you have a bunch of empty space here, you then say that from voxel, whatever this is, like voxel 10 to voxel 16, or from voxel 10, you then have like 6 entries of empty space, which leads you over to here. And then you have over here, this is maybe like voxel 30 or something, if we translate it to... we translate the 3D position to a 1D position. You could do something like that, and then you could like, skip the entire thing like that. And it's also kind of like one thing that I'm still unsure about is really, and I feel like people talk about it in a way where it's like obvious, and but I really think that it isn't, which is how to handle not storing things in memory, right? Because one of the difficulties here is that you have like let's say you have a world that's like 300 voxels tall. Like 90% of your world is going to be underground. It's going to be things that don't exist. So ideally, you wouldn't really want to store that in memory unless it's visible, right? And I don't really understand how to do that, because I feel like it would have to like exist within the buffer in a way that makes sense with like indices and stuff. So that's really strange to me. That's way well beyond me. I know it's doable. I've seen people do that, where they like shoot a ray and then they like find something and then they load it in. I don't know. I mean, that's octrees are supposed to work that way, I think, but I still don't understand how you actually like load that into memory. But marching cubes, eh? Oh yeah, I was gonna look up here's another one, transvoxel algorithm. The transvoxel algorithm is a method for seamlessly stitching together neighboring triangle meshes generated from voxel data at differing resolutions, so that level of detail can be used with large voxel-based datasets such as volumetric terrain in next-generation video games. The algorithm was invented by Eric Langiel in 2009 and implemented in the C4 engine. Oh, Nightchild, how's it going? I'm just reading up about marching cubes, really. I'm leaning towards just getting a marching cube solution here. But I'm reading about the trans-voxel algorithm now, which is supposed to be an extension of that, I think. Trans-voxel algorithm works by inserting special transition cells in between regular cells along the boundary between voxel data sampled at 1 resolution and voxel data sampled at exactly half that resolution. Trans-voxel is marching cube with LOD? Yeah. Yeah. Because yeah. I was kind of yeah, I did look at dual contouring, or I tried to, but I don't know if I really found anything. I didn't really look into it that much. I watched the talk about from the Finnish guy yesterday, which seemed good, but I wasn't sure if it was a fit for me. I can look at dual contouring again. Because as I've been talking about now, I was kind of thinking marching cubes wasn't a solution for me, because I thought marching cubes was more rigid, where it was just, you know, creating a rigid transition from one voxel to another, but it seems to actually support varying levels of like volume for each voxel. So I think it's actually completely viable. I see the volume. Don't worry about the link deletion thing. See it. How to create a sharp mesh from a function. So yeah, I actually looked at this. Dual contouring works by placing a single vertex in each cell and then joining the dots to form the full mesh. I did actually read this article, I think. A lot simpler algorithm. Radiant. See, the number one difficulty with reading any article like this is the words. There are always words that you have to know what they mean. Like when I was reading about marching cubes before, it was like isosurface here and you know, that kind of stuff everywhere, and isosurfaces and scalar values and I didn't go to school for this. I don't know. In marching cubes, we just needed to evaluate the function. I don't know what that means. F, S, on a grid. And now we need the gradient information, and not just on the grid points, but at certain points in between as well. While there are a number of sources of this information, by far the simplest is to start with the function F that can evaluate it in any point in space. We can then calculate the gradient information using calculus or numerically. Note that the gradient is often called the normal or Hermite data, which are similar concepts. This works for any sufficiently smooth f, providing you pick d small enough. In practice, even functions with a sharp pointer are sufficiently smooth, as you don't need to evaluate the gradient near the sharp parts for it to work. Link to code. Adaptivity. So far we've just got the same sort of step look that the marching cubes had. We need to add some adaptivity. For marching cubes we chose where along the edge. There are a lot of missing 2s and stuff here. We need to add some adaptivity. For marching... Sorry if you wrote this, I don't mean to criticize you. I don't know if you did. You could have. For marching cubes, we chose where along the edge to put a vertex. Now we have a free choice of anywhere in the interior of the cell. No, it's actually pretty good compared to a lot of the other marching cube ones I read. There's just a lot of missing. I don't know what the words are in English. Prepositions, proverbs, to and those kind of things. I don't know. Instead, we load gradient information for those points. The dual contouring vertices will be placed at the point inside the cell that is most consistent with those gradients. But marching cubes would be more detailed, wouldn't it? I don't know if it's gonna continue. More natural look and flow to it than marching cubes. In this sphere, that's not a sphere. I mean, the reality is I don't need it to be like super accurate. I'm like, I would be okay with it if it just draws like 2 triangles for me. More or less. What? Quadric function. We're picking penalties. See, this is what I mean. I'm like, I'm usually pretty good at just going with it. Like when I read stuff like this and they just use words. And I'm just like, okay, that's a word. Maybe I'll pick up on what that word means. But problem is even worse in 3D when there are likely to be a lot of normals. The way to solve this is to pick the point that is mutually the best for all normals. First, for each normal, we assign a penalty to locations further away from ideal. Okay, so this is kind of like when you're doing pathfinding and you give like certain things a certain weight to it to make it less likely to go there or some shit like that, kind of. So the idea here is that the darker it is, the less likely, some shit like that. We assign a penalty to locations further away from ideal. Then we sum up all the penalty functions, which will give an ellipse-shaped penalty. Finally, we pick the point with the lowest penalty. Something like that. I'm not really sure if this is... This feels like it's just a visualization of what we're doing mathematically. Sum of all those squared terms is a quadratic function, so the total penalty function is called the QEF. 4 edges and each has a normal, which defines that white line of where the vertex within the grid could be placed. Right. Yeah. And that's how we find this. I think. Surface nets. Other dual contouring annoyance is that it can sometimes generate a 3D surface that intersects itself. For most users, this is completely ignorable, so I have not addressed it. There is a paper discussing how to deal with it. Okay. You can run it on an octree to have varying sizes of cells precisely where you need the detail. The rough idea is identical. Pick a point per cell using sampled normals. Then for each edge showing a sign change, find the adjacent 4 cells, combine their vertices to a face. With an octree you can recurse to find those edges and the adjacent cells. Another neat extension is that all you need for dual contouring is a measure of what is inside/outside and corresponding normals. Though I have assumed you have a function for this, you can also derive the same information from another mesh. This allows you to remesh, i.e. generate a clean set of vertices and faces that cleans up the original mesh. For example, Blender's remesh modifier. You can start with just a vertex at the center and you will end up with basically a voxel grid. But at that point you have already the dual contouring mesh, so finding the ideal position is like smoothing the voxel space. Right. Yeah, I don't really know. Because it sounds very similar to marching cubes. So I don't really know which direction to go. So I feel like, yeah, I could implement both of these. It's or either of these. It's just putting in the time and effort to do it and figuring it out. It's just a question of like, are there any difficulties? This either seem like they both seem to actually do what I want, and marching cubes do not seem to be as memory heavy as I thought it was. It's like 32 bits for the marching cube implementation. For the voxel data, I think. And that should be fine. Okay, marching cubes. Issues, complexity. Even though you only need to process one cube at a time, marching cubes ends up pretty complicated as there are a lot of different possible cases to consider. But this isn't really relevant, is it? Because this is already solved. So this shouldn't really pose an issue. You just copy paste the solution and then you're done. Some cases in marching cubes cannot be obviously resolved one way or another. In 2D, if you have two opposing corners, it's impossible to say if they are meant to be joined or not. Ah, fair enough. In 3D, the problem is even worse, as inconsistent choices can leave you with a leaky mesh. Marching cubes cannot do sharp edges and corners. Oh. Okay. Yeah, that kind of sucks. Yeah, that's not good. Maybe this is the direction then. Because I feel like I need the ability to be able to tell it whether something is smoother or sharp. Kind of. The dual graph. A lot simpler algorithm. Dual contour 3D. So this doesn't use like a massive lookup table or anything like that. This just kind of calculates it on what kind of data structure would this end up with, right? Like, do I do this on the CPU or do I do this on the GPU? So I'm not really sure. Like one issue that I have been mulling over a little bit is the fact that my actual logic implementation also has to work with the rendering solution, kind of. Because if I'm walking, I have to be able to walk up a slope, for example. Like, that's doable. Just using, like, logic, but I'm just thinking if there's like a way to create a mesh that you can actually interact with for logic and stuff like that. And then you'd get a mesh. That's where I'm a little confused. Like, are we even Raymarching anymore with this? I guess each, because I feel like you can do both, maybe. Like you can mesh it using this solution, and you can mesh each voxel and then Raymarch into the voxel, and then do a ray intersection on the voxel. I mean, either way, it's meshing. You have to do meshing some way or another. I guess it's the difference between are we rasterizing it or are we marching it? Oh! It's just right now I'm generating them using just the voxel matrix on the GPU side. That's where I'm generating the triangles at the moment. Which is like kind of why I was looking into marching cubes, because it would mean that I don't have to calculate neighbors and shit like that. That can already be pre-calculated. Fuck me. Let's see. Dual con touring C#. So many files. Damn. I don't even know where to go. This is why I just put everything into one file almost. Game manager. Build Octree. Generate mesh from Octree. C++ implementation. Oh. Draw octree, draw octree. Givens. I think it's happening in the octree. QEF solver. Mesh. Reading other people's code is just it's tough. QEF data. Drives data from the original DC implementation. Drives the contouring process. Edge VMAP. X-axis, Y-axis, Z-axis, edge mask. Vert map. Face map. Jesus Christ. Cell proc face mask. What are we doing here? Simplify octree. No. I'll be honest, I'm not really getting anything out of this. This is the code there. Find best vertex. F normal, XYZ. If not adaptive, whatever the hell that means. Evaluate F at each corner. BNP.empty. For each edge, identify where there is a sign change. There are 4 edges along each of the 3 axes. Yeah. Honestly, I'm gonna have to look into this more. I don't feel like I have a good enough understanding to begin implementing it. Iterates over a cells of size 1 between the specified range, evaluates F and F normals to produce a boundary by dual contouring. Returns a mesh object. Okay, this is the true. Find best vertex. This is the thing with the penalty, I think. This part. Perhaps. And this is the actual dual contour. This is a 3-dimensional for loop, I think. Something like that. Or it's a for each, I'm not sure. Find best vertex. I don't know. I don't know what F range is. Start, stop, step 1. That's a for loop. With a step size of cell size. Something like that. For each cell edge, emit a phase between the center of the adjacent cells if it is a sign-changing edge. All right. We didn't get any programming done today, and it's been a kind of short stream, but reading all these documents, I'm cooked. I'm gonna keep looking into dual contouring and try to figure it out, and then we'll try to implement it. But yeah, we'll see. I do think this is the way, though. Probably. Marching cubes seems like, on the surface, marching cubes is the solution, but the fact that it does have all of those caveats means that it's not the solution. I feel like you'd have to implement a bunch of new edge case solutions for it to be able to just render normal things. It's not really meant to, like, it's not meant for video games, not really. So you'd have to modify it for that. It's meant for medical data, and that's not really meant to show those kind of sharp edges. I mean, you can use it for other things too, but I think that's what it was designed for, more or less. Or if you don't want sharp edges at all. If you use sufficiently small voxels, then you can kind of have sharp edges. Almost. But not really, I think. Anyway. I'm gonna go and read about this and eat some pizza or something, and hopefully next time I'll have a game plan to try to figure this out. Otherwise, I'm just gonna flounder around a bit and try to just do something and see if we can start trying to implement it. Because my current solution is just bad. Like, it's just straight up bad. It's just a really ham-fisted way of doing marching cubes, kind of. So, yeah. Until next time. Thanks for hanging. Have a good night. Bye-bye.